All right, so this is the water quality analysis of the Harpeth River State Park done by the Instrumental Methods of Analysis Lab at Lipscomb. So the Harpeth River is 125 miles long. It starts in Eagleville, which is right outside of Murfreesboro in Rutherford County, and it flows through a lot of cities and counties, including Nashville. So it's a tributary of the Cumberland River, and it has a really high species richness. So since 1999, the Harpeth River, it's been on the impaired water list by the state because damage to the river has occurred by sewage, withdrawing water, and increasing stormwater runoff. Also, low levels of dissolved oxygen due to high concentrations of other nutrients, which mainly is phosphorus. So the purpose of this lab was to evaluate mineral and metal content to see how healthy the river is. We compared it with previous data from Radnor Lake, Long Hunter State Park, Montgomery Bell, and Harpeth River State Park data all from 2011, 14, and 12. So the metal and ions will indicate if there's any impact from fertilizer or pesticide. So we collected water from sites in Franklin and then all the way to Cheatham County. So the sites in Franklin were, I think it was, Pinkerton Park and Eastern Flank and the rec center. And then the spots that we collected near Kingston Springs were off of the kayaking route. So we did the Narrows and Highway 70. So this was our group, just a nice little family photo. This was the Eastern Flank, which was the most southern location in Franklin. Pinkerton Park, the Highway 70, there's the Harpeth. Now Stephen can take it over.
So moving on to the procedure, we visited the Harpeth River Canoe Access Points in Franklin on the 19th of September and collected samples from 3 different locations, which was upstream from the downtown area, near the downtown area, and then downstream from the downtown area, which included downstream of the wastewater treatment input. The samples collected from the 3 places.
September 25th.
On September 25th, okay. So we collected about half a liter from each site, and we measured the pH and the conductivity in the field. We filtered the water samples to remove any solid impurities such as rocks or dirt, and we separated them into 2 different samples for ion chromatography and for inductively coupled plasma optical emission spectroscopy, which will be known as ICP for the rest of the presentation. For the ICP samples, we added about 4 milliliters of acid to the 100 milliliters of water to preserve the samples over the course of time. So just a little bit of background on ICP, optical emission spectroscopy. Essentially, a liquid is sprayed into hot plasma, which then allows the sample to emit light at various wavelengths, and the wavelengths that light is emitted corresponds to what elements are in the sample and at what concentration those elements are at. So that is a little bit of background on ICP. This is just a little bit of a diagram of an ICP. One fun fact is that the argon gas that makes this ICP torch is actually hotter than the surface of the sun. This diagram shows how our samples enter the plasma and the temperature of the plasma at different heights. We're about to show you a video that should show you the ignition of the plasma. So this is our ICP at Lipscomb. On the bench next to the computer is an auto sampler that allows us to run samples continuously. The water samples are located there at this moment. A robotic arm inserts a needle into the sample and pumps some of the sample into the ICP nebulizer. And the nebulizer is what atomizes the sample for ICP usage. And then the ICP plasma torch and nebulizer are located behind the window that you see on the top right of that machine. We also used ion chromatography along with ICP. This is a schematic of an ion chromatogram. We have a solvent and mobile phase that is represented on the left of this diagram, and that is pumped through the system. The sample is introduced with a syringe by a robotic autosampler. The sample and the mobile phase enter the ion exchange column where ions are separated on the basis of charge and size. The flow enters a couple of suppressors to reduce background, and then the flow goes into a conductivity detector where the signal of various ions are detected. Since ions are charged, we can measure the conductivity to detect the presence of these ions. This is our Dynex ion chromatograph at Lipscomb. As you can see, the solvent and mobile phase is in that bottle with the red cap on the top, and the pump is on the right. In the middle is the ion exchange column. That's kind of where the magic happens. And then the samples are currently sitting on the bottom left. This was the ion chromatogram, which is a sample ion chromatogram from the Montgomeryville State Park area. It displays the peaks of ionic species such as sulfate, phosphate, nitrate, bromide, nitrite, chloride, and fluoride as they exit the column. The height and width of those peaks correspond to the concentration of the ion. Taller and wider peaks correlate to higher concentrations. So we're going to move on to our results. These are our ion chromatography results from our different samples. There are a lot of numbers on the chart, but the important ones to realize are the ones that are in red, and those are the ones that are just a little bit higher than is typical, and that would be the phosphate concentration at the Pinkerton Park sample site. Sulfate is also a little bit elevated at some places. Sulfate concentration is an environmental concern, but for drinking water, sulfate should be below 250 parts per million, and the concentration of sulfate are much lower than the 27 to 50 parts per million in the Harpeth River samples. Phosphate is at 0.5 at the Pinkerton Park, and it's a little bit higher than the recommended level for rivers and streams, which is 0.1 parts per million. These are our ICP results, which measured the metals and minerals. The numbers are low, mainly insignificant. We didn't have significant amounts of metals such as iron in the water. We do see a trend where the concentrations were lower for the western sites, such as the Narrows. As you can see, potassium is a little bit elevated in the Pinkerton Park area, as well as phosphorus. And at the Williamson County Rec Center in Franklin area, that phosphorus concentration is also a bit elevated. So moving on, we're going to be looking at the calcium content by IC and ICP. As you can see, the calcium concentrations in the three sites in Franklin were a little bit higher than the site at the US Highway 70 bridge, the Narrows of the Harpeth, and the Narrows waterfall. Moving on to the nitrate concentration, those were also highest in Franklin. The highest nitrate concentrations at the Williamson County Rec Center downstream from the wastewater treatment plant in Franklin do make sense. Elevated levels of nitrate may be indicative of fertilizer or contamination with petroleum products. The maximum containment level for the EPA is 45 parts per million for nitrate in drinking water, and this is well below 45 parts per million. Moving on to a little bit of the discussion of our results, the important thing to note is that the water is clean in simple terms, but we are seeing some potential impact from fertilizers or human contributions such as ammonium nitrate, phosphorus, sulfur, which are all below the maximum containment levels, even in Franklin, which were a little bit elevated. The levels of phosphorus, the phosphates, sulfates, are higher at the sites in Franklin versus at the Harpeth River State Park. So going on to water hardness, which is essentially a determination of the calcium concentration. We see that moderately hard water is between 60 and 120 parts per million. Hard water is classified as 121 to 180 parts per million, and very hard water is above 180 parts per million. So we see that the Newsoms Mill, according to our previous data from 2014 and 2016, Newsoms Mill's collection site had very hard water. In both 2014 and 2016, Hidden Lake's water softened from the very hard classification to 120 parts per million, which would classify as just the normally hard concentration in 2016. And then there were also softenings of the water at Highway 70 and the Narrows River between 2014 and 2016. So the water hardness at Radnor Lake in 2011 in Montgomery Bell State Park, the average calcium carbonate hardness at Lake Radnor in 2011 was 195 parts per million, which would classify as very hard, averaging over 13 collection sites. And some sites at Radnor had a hardness level well over 300, which is well over 120 parts per million above the classification for very hard water. The average calcium carbonate hardness at Montgomery Bell State Park in 2014 was 77 parts per million, which would classify as moderately hard. So the maximum containment level goals from the Harpeth River sites. The concentration of fluoride was 1, which is below the 2 goal. The concentration of chloride was 15, and the maximum containment level goal was 250. As you can see on down the chart, the rest of those for nitrate, nitrite, phosphate, and sulfate were below the maximum containment level goals for all of those minerals and ions. As you can see, this is IC data, ion chromatography data from Radnor Lake in 2011 for the same different ions, chloride, fluoride, nitrate, nitrite, phosphate, and sulfate. As you can see, all of these are below the maximum containment level goals. We would classify those as safe for Radnor Lake in 2011. So we would like to acknowledge Dr. Klinger, as well as the Harpeth River State Park staff. Not on this slideshow is also our lab instructor, Dr. Verne, and the rest of the Lipscomb University Chemistry and Biochemistry Department.